number 7 over here. So x squared plus y squared. And then what do I have? I have plus x minus y minus 3. Plus x minus y minus 3 is equal to 0. I'm going to do the same approach. I'm going to get the x squared plus x. Put the y's over here, y squared minus y, and move the 3 over, the minus 3 over to the other side. Okay, so let's complete the square on this one. What do I do? Okay, here I take the coefficient from the x, divide that by 1, square that. So I divide that by 2, square that. So I'm going to add in 1/4 over here. And then I come over here and do the same thing for the y's, but again, I've got to add 1/4 to both sides. Make sure I do that. Now do the same thing over here for the y, and this is going to be another 1/4. So I take 1/2, or minus 1 divided by 2, square that, I still get 1/4. I get plus 1/4. Okay, that means I can factor this into x plus 1/2 quantity squared. X plus 1/2 squared. This factors into y minus 1/2 quantity squared. And on the right-hand side, I have, this is 3 1/2, which I can write the 3 as 6/2, and then add that to it, so I get 7/2. So this is my equation. So I have my x plus 1/2 squared plus y minus 1/2 squared is 7/2. So the center of this circle is at x is negative 1/2, y is positive 1/2, and the radius is equal to the square root of 7/2. That's all. Works with a little bit of fractions over here. And that's the standard form, and you have r squared on the right-hand side. But that's how you complete the square. Get all the x's together, take the coefficient in front of the x, divide it by 2, square that, add it in, and it factors into that number that you got, x plus 2 quantity squared. Or this number here when we got y minus 4 quantity squared. Same thing over here. Here you just had some fractions to deal with. These are integer values, those are fraction values. So you have both of those to, in this case, contend with there. So any other questions in that range of things over here? Okay. Anyone have any other questions there? Anything else you want to see? That's all it is. Hopefully it's not too complicated. Are we fine with that? Okay, so those are our circles. That's when you take your cone and you intersect with a plane that kind of slices through the cones, and you have a circle of different radii. And that's all it is as you go down. Okay. Then the next thing is if you take that plane and tilt it at a certain angle, so it's no longer touching one side of the cone. It misses a complete side of the cone. It only gets a fraction of it, and it gives you a parabola. And we started by giving you the geometric definition of a parabola by taking a focus and a line called the directrix, and then making sure the distance between the focus and a point on that curve and that point on that curve and directly down to the directrix is the same. It's always the same. And then when you do that, you trace out something like this, something like that, or like that. So this is all now about parabolas. And it's interesting to see how it comes from a very simple definition and you need to understand the concept of distance well. And I went through and showed you how to derive those different sort of formulas for it. Because you have, like, in this case, you have a parabola that opens upwards. And here's the focus here at 0, comma, p. And then over here, this is y is equal to minus p. It's opening upward. And you're comparing this to, you know, my, in this case, I think it was like x squared is equal to 4py. This is the general form. If it opens downward, it looks more like this. Y is equal to plus p, and then 0, comma, put a negative p, even though p, we can use a negative number, opens downward like this. Should be symmetric about that. And you get x squared is minus 4py. So opening upwards is positive, downward it is negative. And you can also open side to side. So there's many different ways in this parabola can be set up. It could open this way. And over here, this is my, you know, in this case, p comma 0. And over here we have x is equal to the negative of p. And the equation for this then is y squared is equal to 4px. And then you open the other way, and you can actually look at it like this. So now the parabola is opening this direction. Still centered at the origin. I decided to keep everything centered at the origin to make life a little bit easier. So it's negative p comma 0, and x is equal to a positive p. So when you're given a parabola in one of these forms, to analyze it, it means you want to find the focus and the directrix. That's what it means to analyze a parabola. So any questions in 12.2? Anything there that you're not really sure on how to do? Now, hopefully you can see where the 4 comes from. That comes from making those two distances are the same. And you're going to get a 2p and a minus 2p on one side. When you add that 2p, it becomes a 2py, and minus 2py becomes a plus 4py. Any questions? There's only a few. Just have a couple of short questions in 12.2. So what's the objective here is to essentially find p, and then that should lead to your focus and your directrix. Now the focus is interesting because if you know what a parabola is, when you make mirrors and say, you know, sound or sunlight comes in, when it reflects off of this, they always end up, no matter where it comes in from, it always ends up at the focus. Now, some concert halls, it's also designed for the same as sound waves. Some are more elliptic in shape, and they may have a couple of focal points. But the focal point is kind of a point of magnification. So if you're looking at observing the planets or the stars, they make parabolic lenses to take the light wave that is scattered and then focus it, so then you can kind of see it magnified and you can see what's going on. Now, some people in certain concert halls, they sit in certain locations and you can actually hear, you know, if you're at a focal point in a concert hall and you hear people whispering, you will hear them very clearly as if they're sitting right next to you talking. Everything else is quiet because all the sounds will come back and they'll just focus at that point. And they also make those things when they want to. They make the parabolic, you know, cones that'll kind of listen to you from a distance. Same principle there. They have a parabolic, sound comes in, and then they have a sensor here that kind of magnifies and listens to that sound because it's already magnified. You magnify the top of it. Well, parabolas are very interesting. They're all done from a geometric argument, meaning the distance from this distance, and I don't have it drawn to scale here, that distance, those would be the same. So D1, D2, you always keep D1 equal to D2, and that defines the shape of the parabola. As you're moving along here, these should be the same. They're not shown to be that way, but they should be. So, any questions on any problems in that? Anyone think they can do that? No problems there? Okay.
I didn't get any of them, honestly. I didn't really understand 12.2.
Okay, so let's give me some problems. Just say, problem 1, 2, 3, or 4, whatever.
Yeah, 1, 2, 4.
Okay, let's start. We'll take a look at number 1. We'll use these as our guide. We want to analyze these parabolas. That means, as I said, finding P to identify the focal point and finding the directrix to identify the line that defines that parabola. So those are the two geometric features that define any parabola. So if you're going to analyze it, you want to find those features. So let's take a look at number 1. So here we have y is equal to 4x squared. Now what I want to do is I want to compare it to one of the 4 different types. This was going to tell me which type do I compare it to. Well, here it looks more like everything's positive. This is type 1, okay? So in general, I'm going to compare it to the following. On the other side over here, I'll compare it to what I have over here. I have x squared is equal to 4py. I just switched it around. Or I could write it the other way. This is equivalent to 4x squared is equal to y, which if I write it that way, I get the same thing. X squared is equal to 4py. The objective is very simple. I want to find p. So my objective in all these problems is to solve for that parameter p. Over here, let's solve this. Take this one, this is easy. I'm going to divide everything by 4. So what do I get? I get x squared is equal to 1/4 y. Okay. From here. But that has to also be equal to the following, because this is x squared, so it also has to be equal to 4py. Well, the y's cancel out. I can solve for p. And this tells me then that p is 1/16. Divide both sides by 4. Okay, so what does that tell me? It tells me where my focus is. So for this type over here, my focus is 0, p. So here's the focus of that. 0, 1/16. And it also tells me my directrix. And that in this case is y is negative. It takes the negative of that 1/16. So if I was going to try and sketch this a little bit, let's zoom in over here. And let's say 1 is way up here. So here's my focus over here at 0, 1/16. So this is only 1/16. And I come over here, the same distance here is the same distance right there. And that's why y is equal to negative 1/16. Then my parabola is going to be the locus of points that keeps the distance from here to the parabola, and that distance to essentially that distance the same. So it's going to look something like that. So this is my, distance here. This is D1, that's D1. I have D1 or D2. I always have distance 2 is equal to distance 1, and that'll define the shape of my parabola. It's all I need to define the actual shape. This as opposed to that way or some other way. That P is the only parameter that defines everything you need to know about any parabola. And then you can set up exactly where the focus is, where the directrix is, and essentially what I'm saying is the length of this distance and this distance have to be the same. That's how it's defined. It's actually defined geometrically. Now, those two distances have to be equal to each other. So 1 is way up here and -1 is way down there. Okay, so that's number 1. I'll leave these up here so we know what to choose from. Let's take a look at problem number 2. Now it takes a second to kind of go through these. So in all cases here, the focus is the, no pun intended, it's the parameter P, which is the y coordinate or the x coordinate, depending upon how it's set up, of your focus. So number 2 looks like the following. Y is equal to a negative 3x squared. Okay, now it's negative, so now we're kind of looking at this. They have opposite signs over here. 2 positives with an x squared, so 2 positive with an x squared, it's, this one, and then a negative and a positive with an x squared, it's that case. So in this case over here, we're looking at this option number 2. So let's compare it. So this is what we're comparing it to. So this is going to be compared to this form. X squared is negative 4py. So what I can do is I can, if I wanted to, I could solve both of these for x squared and set them equal to each other. So over here, if I flip this around, this says my x squared is equal to a negative 1/3 y. So I just divide both sides by -3. Well, that's also equal to x squared. So this has to be equal to a negative 4py. Okay, so the y's cancel out. And I can solve for p. And this tells me then if I divide both sides by a -4, tells me p is a positive 1/12. Okay, so what does this look like? So now I go along, and what happens over here, since this is negative, I use a negative value for p. So it actually comes down to the origin. It should be right here, excuse me. Oh, keep me awake. Talking and writing, not thinking. So what happens over here, it's going to go through here, but I go down to this, and I'll put it over here as a x is 0, y is negative of p. For this, it's always the negative of p is your coordinate there. So it's 0, negative 1/12. And then I put my directrix over here, my line, if you will, and try and keep that the same distance there. So that's y is equal to a positive 1/12. Now I want to keep the distance from this point to my curve the same as to my line over here. So it kind of looks something like this. Very similar to the other, it just opens downward. And what you're doing is you're making, should be a little flatter, but you're making this distance here. I'll do it in green so we have a better picture of what's going on. Making this distance equal that distance. Making them equal and keeping them equal, that'll define the shape of that parabola that now opens downward. This is its focus, there's the directrix. And this should be perpendicular here. I don't have it drawn that way for the angle. But that's all it is. Everything is about P. And then once you find the P, what case do I have and how do I set it up? Let's take a look at number 3. You see, you have one of each type there, essentially. Now, I don't put a lot of problems on this. I want you to see it and get exposure to it, but you don't see it too much in the actual calculus because we deal more with functions, and these are not set up as functions. They're just, as the word says, they're conic sections. Let's take a look at number 3. So we have y is equal to 1/4 x squared. Well, we don't have any of the other types. I should probably put some in there. So we have y is equal to 1/4 x squared. Try that now. Try that yourself and see if you can find the focus and the directrix just by looking at that. This one's a little bit easier. I'll give you a second to try it. Is everyone getting p is equal to 1 in this case? Very simple one. Anybody want to see that worked out? That's an easy one. So here's my focus, 0 comma p, directrix y is equal to the negative of p. Everything is positive, parabola that's opening upward. That's all it is. So we're just focusing on these two types. Those are the more common ones. These are actual functions. Those are relations. They don't pass the function test. So does everyone kind of see that? It's all it is just finding the p. Fit it to the right, model, and solve for p. If I was going to draw what this would look like, again, it's going to open upward. So I get this is 1, 0 comma 1, and here's -1. They're about there. It's going to start at the origin right here. And you want this distance from point over here to the line over here to be equal to that distance. So it's going to look, actually comes down a little bit more. It kind of parabola looks like that. And here's my D1 and D2, and you have to establish that they're always equal. And that'll define the shape of that parabolic shape right here. Everyone's kind of see that now? Anyone not following suit? And let me have you try the last one on your own. We have y is equal to a -1/8 x squared. So carry through and do the same thing to that. Now you see the parabola is going to be opening downward, different sides. Oh. Add, focus. -8y. There's one. rewrite this. What's equal to, excuse me, 2. I thought I was doing it opposite in my head. So for these to be the same, P has to simply be 2. So it's a half, but I kind of flipped around in my head. Okay, so once we have that, we can find its focus. The focus is now underneath the x-axis. So it's x is 0, y is -2. The directrix is, above the x-axis, y equal to a positive 2. Okay, so just have to compare it to the right form. Solve each of those for x squared. When are those equal? When p is equal to 2. 2 times -4 is -8. So that's all it is. So I come over here. Focus down here is -1, -2. And here's the line, y is equal to +1, +2. Want to make sure the, distance as I'm kind of going this direction here. So here's the distance. The distances are equal. And as I go this way, my parabola will look like that. So this distance here is equivalent to that distance there. And you make them equal. So it's kind of like you have a string and stuff, and you make sure that these distances are always the same. You can always take a pencil and sketch it out there. That's all it is. Any questions on that? Because it says, what is the geometric quantity that is defining this thing we call a parabola? Because you describe it in words. It's very simple description in words from the text. A parabola is the locus, that means the set, of all the points in a plane, equidistant from a fixed point and a fixed line. The fixed point is called the focus, and the fixed line is called the directrix. That's all we're defining here. And we use the distance formula to get this formula over here. So that's where this thing came from, by making sure from any generic points on there with a generic focal point of, in this case, either 0 comma p for the one that opens up, or 0 comma -p for the one that opens down. And you can do the same thing for left and right. Instead, you're going to have y squared and x's. That's the only difference. That's it. Not, too complicated. I'm trying to keep it extra simple. And the other, 125, you might also move this off the center. So then you have a little more complication because you have y minus k, x minus h quantity squared. So instead of being here, it could be shifted around. Then the directrix shifts, the focus shifts, everything shifts based upon how these are shifted. I'm not making it that complicated because I don't want to go into a lot of detail here. It's not as critical. But any questions? Is this okay for everybody? I don't think you got it. The next time is an ellipse. Then you have 2 focal points, and you want to make the distance, the fixed distance, not equivalent, but the distance from one focal point to the graph to the other focal point is always constant. That's always the same. That's a little bit different. So for the ellipse, you get a different sort of picture. And then you derive the equation that defines it based upon those two pieces of information. Now, we are centering, just like we centered the circle initially at the origin, we're also going to center the ellipse at the origin. So if you come over here, here's your origin. And you take one focal point here. And the other focal point is at an equal distance. These are the same distance over here. And it's almost like, you have a piece of string that connects everything together. You have a fixed length string. You take a piece of string of a fixed length, and that's always the same fixed length. And when you start tracing it around, you'll see you get something that looks like something like this. Kind of like a football, if you will. Should be a little more symmetric over here. And this distance plus that distance is always the same. This is a fixed string, and you just have a pencil attached to it, and it'll kind of go around like that. And that'll give you an ellipse. Now you have two foci. So that's what you're looking for, the two foci. And your center is at the origin. And it's given in a word description. So you can kind of see the word description for an ellipse. It's a locus of all the points in a plane, so it's the sum of the distances. This distance plus that distance from 2 points, fixed points, remains constant. So this plus this is my D1, and here's my D1, D2, D1 and D2. So D1 plus D2 is always a constant, like a fixed length string that doesn't change. You just put your marker or pen there, and as you keep it taut, it will kind of trace out. Should be a little more symmetric over here. And it'll trace out a picture that should be symmetric this way and that way. And that's what the other one. And then you'll deal with the hyperbola. But we'll have more time tomorrow to go to the ellipse and maybe a little bit more on the hyperbola. And that's it. Just to recognize what these conic sections are. Circle. And then, a kind of degenerate circle is an ellipse. It could have a major axis along the x, or it could be narrow in this direction, because you can actually have an ellipse that goes this way. Your foci could be on this axis over here. So your ellipse could go this way. Major axis along the y, and your minor axis. So you have circles, parabolas. We can open it that way, that way, that way, that way. They can even parabolas. We're not doing it, but you can easily have a parabola that kind of opens like this on an angle over here. We're not going to do that. We're going to make it simple. Because you have all these ways of manipulating these conic sections around. And then the other case is if you take the two cones and you cut them this way with a plane, and you take that plane and look at where they are cut, you kind of look over here, you get hyperbolas. And almost like two parabolas. It's not quite, but they're similar to two parabolas are combined together. You have this, and you have a cutting over there, so you're up and down, and that's what you get. And we'll look at that on Thursday, as well as maybe look a little bit of this on Thursday, as well as the last topic, which kind of related to the quadratic formula. And there is a relationship there. That's why I want to do it. It's called the classification theorem of conic sections. And where it's interesting, for those that stay on in mathematics, you're going to see the classification of partial differential equations. There's going to be some that are going to call parabolic, and some are going to be called elliptic, and some are going to be called hyperbolic. It's related to this, and it's related to what's happening. That's why I just want you to be aware of those things in a future math course beyond the calculus. It won't come up in the calculus unless you're in advanced calculus, and then they'll start talking about it beyond. You do regular differential equations, then they'll do what we call partial differential equations. If you're doing any scientific discipline, you will see them in your junior year PDEs, what they call for short. Okay, but any questions on that? So just giving you a different perspective of how to analyze something, mainly through a geometric definition. Taking two distances, fixing them, and finding the locus, or the set of all the points, contiguous points that are on that graph of that locus of points. Okay, any other questions? Now, Jay, you can just graph those trig functions and then you can read them off of Desmos. I'm using that as a nice little tool. You can do the same on your calculators, but then you have to actually solve for those. That's a little bit harder to do. That's why I'm going to allow you, and I want you to get used to using that tool, Desmos. It's a nice little tool. So even if you take a calculus course where it's not allowed, you can use it on your homework to get a better understanding of how things work. And then also look at your calculators to see if you understand that too. But it's a good visualization tool for understanding things. A picture in calculus is worth 1,000 words. It's a very visual type of course, because you're seeing rates of change and you're looking at how things change and you get a visual image. You're looking at max and mins and everything else. Then you're looking at the area